So I've started the recording already. Are there any questions from what we discussed yesterday? So yesterday we were discussing this proof, right? We wanted to complete the proof of lemma 2, which says that if the distance is the same for two flows, f and f prime, between the source and the target, then this z set, right? This is a set of all arcs that participate in some shortest incrementing ST path with respect to that flow. Okay, so this is a Z set with respect to F prime, and this is a Z set with respect to F. And the claim is that the Z set with respect to F prime has to be a proper subset of the Z set with respect to F. Okay. So our goal was to prove this, and as you may recall, I got confused at some point, but then I managed to untangle myself from that mess, and by then it was too late to finish the proof. So let's quickly go through what we did, and then we will look at the point where there was confusion. Okay, so assume that K is the distance between S and T in the flow F. Okay. And now let's say we take an arc which is in Z set with respect to F prime. Okay. So this arc induces an arc UV in the directed graph. So that could be, if A is like this, UV could be in the same direction or UV could be in the opposite direction, right? So that's a key difference to remember between A and UV. Okay. Good. And we are looking at this drawing here, right? We know that this is in the Z set. So what we can do is we can take a shortest path in this set from S to T. And if you do that, then the distance from S to U will be I minus 1, and the distance from V to T will be K minus I for some I, right? Okay, and then we applied lemma 1 to observe that the distance in with respect to the flow F between S and U and V and T, if you add them up, that has to be less than equal to the distance with respect to the flow F prime. So this is where we are applying lemma 1, right? And if you add up I minus 1 and K minus I, you get K minus 1. Okay. So that is a crucial observation that we'll be using later in the proof. Okay. Now let's go back to our main goal. We have taken an arc in this set. So our goal is to show that this arc also belongs to the right hand side. Okay. That will prove that it is a subset, and then we will focus on the proper subset part. Okay. So our goal right now is to show that A is in the Z set with respect to the flow F. Okay. And this is where the confusion started. All right. So let us suppose, for the sake of contradiction, that it is not in the Z set. And this is the part which I was not able to see. So let me try to convince you. I claim that under this assumption, the flow on the arc A must have changed going from F to F prime. When I say flow here, I mean the F of A and F prime of A. This would have changed. Okay. So supposing it does not change. Well, if it does not change, then let's go back to this drawing. There is a path from S to U, and there is a path from V to T, and the distance, if you add up, is less than equal to K minus 1. Remember? This is something we have already proved. And so, if the flow does not change, then what would happen is that UV would also be an arc in the original auxiliary digraph, because it is an arc in the new digraph. So if you don't change the flow, then the arcs between U and V, they don't really change. Think about it. How do you construct the auxiliary digraph from the given digraph? Okay. So in that case, this arc would exist even in the digraph DF. And if that would be the case, then you would get a path whose length is at most k minus 1 plus 1. We are using one more arc, and so that would be at most k. And so that would be a shortest path, and that would mean that A is in the set ZF. Okay? But we have assumed that A is not in ZF. So this is why we would get a contradiction, right? So there is some explanation which I had omitted and I had gotten confused because of the same reason, right? So the flow has changed. Now, how can you change the flow? What does it mean that you change the flow on a certain arc going from F to F prime? How can it be the case that F of A is not equal to F prime of A? Supposing you have a flow F and you get a new flow F prime using the Edmonds-Karp or Ford-Fulkerson algorithm. When does the flow on the arc change? Yes, it has to be on the incrementing path that we chose. And that is why we can say that A belongs to the incrementing path P that we chose. But remember, the path we chose is a shortest path. And so that means that A belongs to a shortest incrementing path. And so again, we reach the conclusion that it belongs to the Z set with respect to the flow F. And that is a contradiction. Okay? Is this argument clear?
Yes.
Yeah. Are there any questions? Anybody would like further clarification? Okay. If not, then let us proceed. So what we have proved so far is we took an arc in Z of F prime and we proved that it is also in Z of F, right? In particular, Z of F prime is a subset of Z of F. Okay? And I had asked you to think about the next step. How do you show that there is some arc in the right hand side which is not on the left hand side? Any thoughts, any suggestions? Anybody has any intuition of what kind of arc will satisfy this property? We want the arc to be in the Z set with respect to the original flow, but we do not want the arc to be in the Z set with respect to the new flow.
Either capacity is full or you.
Right. So I think two of you gave the right answer. It is an arc which is saturated. So either the capacity is full or it has reached zero, right? So either it is a forward arc and you chose the epsilon based on that arc. And so that arc will now be at full capacity, or it is a reverse arc and your epsilon was chosen so that the F value on this arc becomes zero. Those are the two possibilities. And all such arcs will no longer be in the new set Z with respect to the new flow F prime. Okay, so that is what we are going to prove. Okay, so note that, well, I'll say observe that, and I will let you observe it yourself. There exists an arc A on the incrementing path P such that either A is a forward arc on this path. Remember, there is no notion of forward and reverse in a digraph. It only makes sense when you have a path, right? It is a forward arc on the path, and its new flow F prime value is equal to the capacity of the arc. Or A is a reverse arc and F prime of A is equal to 0. Okay? There has to be such an arc. So I will leave this as an observation for you in case you don't see it. Okay? And the hint is think about the choice of epsilon. Okay, good. So the claim is that, well, if the arc is at capacity, then in the new auxiliary digraph, the forward direction will not exist. It will only be the reverse direction. Alternatively, if it is a reverse arc and the flow is zero, then in the new digraph, only the forward direction of that arc will exist. Okay? So the claim is that any f prime incrementing path, incrementing st path, using the arc A, must use it in the opposite direction from P. What I mean is that if in the path P, the arc A was being used from U to V, right? So this is our path from S to T. Okay? The claim is this was in F, right? This was in the directed graph F. Then what will happen in the, maybe I should not say directed graph. I'm looking at the graph with respect to the flow F. I'm looking at the original digraph with respect to the flow F. Okay? Then what will happen in the new digraph with respect to the flow F prime is that on any incrementing path from S to T, you will be using this arc in the opposite direction. It will have to be from V to U. Okay, think about this. Why? Remember, it is a forward arc whose flow is equal to capacity, or it is a reverse arc whose flow is now equal to zero, whose F prime is equal to zero, right? So which means that the direction on which you made the change, you cannot make any change in that same direction anymore. So you will have to, in the auxiliary digraph, only the opposite direction will exist. Okay, maybe take some examples and see what's going on. Okay, good. So now we are going to use this fact to claim that the length of such a path cannot be equal to k. Okay, and here is the way to think about it. What's going to happen is you have to go from here to V, then you have to go from U to T. And on the way, you have to use the arc in the direction V to U. Right? So now we are going to use lemma, the previous lemma. By previous lemma, the length of any such path must be at least I, because, well, you think about this as Vi minus 1, and you think about this as Vi. Okay, so the length from S to V has to be at least I. The length from I minus 1 to T has to be K minus I plus 1. And you need to further use the arc V to U in order to go in this direction. And so that turns out to be K plus 2. So the length of any F prime incrementing ST path has to be at least K plus 2. And so that cannot be a shortest path because the shortest path is length K. Right? And that means that the arc A is not in the Z set with respect to F prime. And in particular, we have found an arc that is in the Z set with respect to F, but not in the Z set with respect to F prime. That means that this is a proper subset of the previous set. Is that part clear? Does everybody see what's going on? We are making use of the previous lemma, lemma 1, multiple times. We used it in the previous part where we wanted to show that it is a subset, and we are now using it again to show that it is a proper subset, right? So we really need lemma 1 in order to prove lemma 2. Are there any questions on how this proof works? Are there any arguments which are not clear? None whatsoever? Is everything crystal clear?
Yes, yes.
Okay. Good. Well, so those two lemmas show us that the number of times you have to do incrementations is order m times n, and each incrementation takes order m time. And so because of these lemmas, lemma 1 and 2, we conclude that the Edmonds-Karp algorithm has complexity order m squared n. Okay. So if there are no more questions related to Edmonds-Karp and the proof of these two lemmas, then we can move on to the next part of this module. Okay. So what we have done so far is we have, remember this module we started talking about disjoint paths and cuts. And eventually we transitioned to directed graphs. We talked about arc disjoint paths and cuts. And eventually we transitioned to flows and cuts. And the reason for that is that flows provide the more general framework to discuss many other problems in theoretical computer science, which have found lots and lots of applications out there in the real world. Okay. And in particular, well, the applications we are going to be interested in this course are graph theoretical applications. And so the next module, the next part of this module, we will discuss the applications of max flow min cut. Okay. So, well, you will be proving on your assignment that using max flow min cut, you can prove Menger's theorem. So the first kind of application is graph connectivity. Okay, so you can prove Menger's theorem using max flow min cut. And in particular, you can prove the edge versions. So the local edge version, the global edge version that we discussed. Just to remind you, the local edge version says that between two vertices S and T, the maximum number of edge disjoint, pairwise edge disjoint ST paths is equal to the minimum cardinality of any ST cut. Okay? And so that can be proved using max flow min cut, and you will be doing this on your assignment too. From the local edge version, you can also get the global edge version, which tells you that a graph is k edge connected if and only if each cut has size k or more. Okay. And well, in fact, what you will be doing on the assignment is you will be first proving Menger's theorem. Yeah, I changed the order in my mind. You'll be first proving Menger's theorem for the arc versions or directed graph versions using max flow min cut. And then you'll be using that to prove the edge version. Okay. You can also go directly from max flow min cut to edge version, but generally it's I think more straightforward to go through the arc version and then go to the edge version. Okay. And not only that, on your assignment, you will also be finding I think it's problem number 3. You'll also be finding an order n to the power k algorithm for deciding whether a graph is k-edge connected. In fact, I have written it more generally. You will be computing the edge connectivity of a graph, which was defined in the assignment. But in particular, you can decide whether a given graph is k-edge connected or not. Okay? And the cool thing about this is that this, oh, sorry, I should not use the same k. Oh, did I use the same key on the assignment? No, on the assignment I did not. Okay. Let me call this n to the power c, where c is a constant that does not depend on the graph. Right? The specific constant you will decide on the assignment. So try your best to get the constant as small as possible while still remaining within the realm of this course, right? So don't apply fancy data structures to get the C down. Okay? So there is a lot you can do using max flow min cut, right? You can basically deal with all of these connectivity issues using max flow min cut. And it's not only edge connectivity, you can also deal with vertex connectivity. And there is some chance that something like that might appear on the midterm exam. I don't know yet. Okay. So it's not just the edge versions, it is also the vertex versions that can be dealt with using max flow min cut. Okay. Good. But now we are going to switch to a different application of max flow min cut. I would have liked to do more applications. Unfortunately, I don't have enough time. I have just another how many minutes? 50 minutes next lecture and 20 minutes. So yeah, I don't think I can do any more applications. Maybe Meghna might have time to do some applications. Okay. So the only application we will be doing now is the application to matchings, in particular to bipartite matchings. But before that, I want to just talk about matchings. So how many of you have actually seen matchings in previous courses? Like not just the definition, but slightly more rigorous discussion of matchings. Has anybody seen it? In introduction to graph theory, we did quite a lot. Wow, I see. Did they also cover algorithms for matchings or just the more graph theoretical stuff? No algorithms. Okay. Okay, good. All right. But there must be some of you who have never seen matchings. So, but the theorems. Okay. So you've seen theorems, which means probably you might have seen Koenig's theorem, I'm guessing. But we will also prove Koenig's theorem using max flow min cut. Okay. Right. Okay, so since there are some of you who may not have seen matchings at all, I'm going to go through what matchings are. Okay. All right. Okay, let's just start with the definition. Okay. So here is an undirected graph G. Right, so now we are back to undirected graphs. Okay. So what is a matching? A matching is something that looks like this. Let me show you a few matchings. So this is, for example, a matching, the red colored matching. This is the green colored matching. Let's look at one more, the blue colored matching. Okay. So a matching is a collection of edges with a certain property. Can anybody tell me what the property is?
No two edges share a common incident vertex.
Exactly. A matching M is a subset of the edge set such that no two edges share a common vertex. Another way to write that is, if you look at any vertex and you look at the cut corresponding to that vertex, then this quantity will be, can anyone tell me what should it be? If you look at any vertex and you look at the cut corresponding to that edge, to that vertex, how many edges of the matching can you see in that set?
0 or 1.
0 or 1. Exactly. Okay, good. So this is what a matching of a graph is. And matchings in particular have found lots of applications, not just in graph theory or theoretical computer science, but much more even in the real world. I'll give you some examples which you can read about later. So matchings have found, just like flows have found many applications, matchings have found many applications out there. And in particular, matchings of bipartite graphs. They seem to have way more applications than matchings in non-bipartite graphs. Okay? To give you some examples that I am vaguely aware of, you can look at the Nobel Prize in Economics. Actually, I have the Wikipedia page here. You can look at the Nobel Prize in Economics in 2012. It was given to two guys called Roth and Shapley. So the Nobel Prize in Economics in 2012, Roth and Shapley. And one of the reasons, well, the main reason for this Nobel Prize given to them was that they used matchings in a, not just in a graph theoretic sense, but also in a game theoretic sense, and with applications to economics and stuff. They used it for organ donation problems. So I think this was in UK, where they wanted to figure out, so you have an organ donation problem which looks like a bipartite graph. So you have a bunch of people who are willing to donate organs, and you have a bunch of people who are in desperate need of organs, right? And you can make a graph out of that. Each donor, well, a donor cannot give an organ to anybody, right? The various biological parameters like blood group and other things that I am not aware of have to match up, right? So based on these parameters, you can decide which donors are compatible with which recipients, right? So for example, donor 1 might be compatible with recipients 1 and 2. Donor 2 might be compatible with recipient 2 and 4, right? And now what you do is you try to give as many, you try to make as many organ donations as possible, right? So that you can save the maximum number of lives and so on and so forth, right? And so this is a classic this is an example of bipartite graphs and matchings in bipartite graphs being used in the real world. Okay, so you can read a bit more about it on Wikipedia or various other sources. Okay, good. And non-bipartite matchings have also found applications, but mostly in more abstract subjects like theoretical physics. So there is a problem called the dimer problem in statistical mechanics, and it basically turns out to be counting the number of perfect matchings in a graph. I will tell you what a perfect matching is in a few minutes. Okay, so there are lots of applications, but we will focus on the main theory. Okay, Good. All right. So here is an optimization problem. Before I pose this problem, I have a question for you. Does every graph have a matching? Look at this definition. Does every graph have a matching?
Yes.
Okay, why?
There will be at least one edge which you can just select. If there is no edge, then anyway you cannot do anything. Right? It's just a subset of an edge set of the edge
Yes.
set. So
So what about the empty set? Is the empty set a matching?
it's a subset of edge set where all the conditions are satisfied. So yes.
Right. Exactly. The empty set is a matching. And so finding a matching is not difficult, right? I mean, every graph is a matching. So that's not interesting. What is interesting is if you go back to the donor recipient problem, what you want to do is you want to have the maximum number of organ donations. And so that corresponds to a matching of maximum size. Okay? So the number of edges is the size of the matching. Given a graph G, compute or find a matching of maximum cardinality. Okay? Good. So that problem is not trivial. Okay? All right. But let's think about something else. Supposing I give you a matching. Supposing I give you a matching and I want to convince you that this is a matching of maximum size. How would I do that? So that's another interesting question. How would you convince someone that a given matching is of maximum cardinality? Rather than saying matching of maximum cardinality, from now on I will just say maximum matching. Okay? So let's start with some examples. Let's take a very simple example. What is a maximum matching in this graph?
Just one edge.
Just one edge. So let's take this edge. How would you convince me that this is a maximum matching?
Because
I mean, I can see in this graph. Yeah,
any edge is incident to the central vertex. So
exactly.
yeah,
Exactly. You've got a vertex, vertex 0. Well, each edge is incident with vertex 0, right? And so clearly you cannot find a matching of a bigger size because every matching, the two edges in a matching, they cannot share any vertex. So if everybody uses the vertex 0, then you can only choose one of them. Okay, fine. What about this graph? What is the maximum matching?
Two parallel edges.
Okay, two parallel edges. How would you prove it? I want an argument similar to the previous argument. How do we prove, how do we convince someone that we cannot take any more edges in a matching?
Every vertex is already covered by this matching.
Okay, that is one way to do it. Right. How about I add more stuff here? Is this still a maximum matching, or can you find a bigger matching?
Still match.
Still maximum. Okay. And now how do you convince me? Now there's a vertex which is not covered. Maybe I'll add one more edge. Now there are two vertices that are not covered.
All edges are incident to vertices 2 and 4.
2 and 4. Thank you. Okay. So here, each edge is incident with one of 2 and 4. Okay. So let's try to generalize these observations. So what we are trying to do here is we are trying to find a set of vertices such that every edge has at least one end in this set of vertices, right? And if we can find such a set of vertices, then it seems, you should prove it yourself, that you cannot find a matching that is bigger than the size of such a set. Okay, so that brings us to a definition. Let me see, do I want to use vertex cover or do I want to use cover? Let's use vertex cover, the standard term. A subset S of the vertex set of a graph. Maybe I should not use S. Let me see. X is a vertex cover if each edge has at least one end in the set X. Okay? And what you are giving me in these examples, here you gave me a vertex cover of size 1, here you give me a vertex cover of size 2. And we are seeing that a matching cannot be bigger than a cover, a vertex cover. Okay? So the observation which I want you to prove yourself is that given a graph G, the cardinality of a matching is always less than equal to the cardinality of any vertex cover, where M is any matching of G and X is any vertex cover of G. Okay? Does everybody sort of see why this is true?
The 0, 1 argument before.
Sorry?
For the cutoff V, there is the cardinality of M intersection cutoff V will always be 0 or 1. So from there we can.
That's right. Right. Each matching edge meets each vertex cover in either 0 or 1. You can view the matching edge as a set of two vertices. And so it will always meet the set in either 0 or 1 vertices, and that actually proves the bound. Actually, sorry. My bad. Every matching, if you view it as a set of vertices, it will have to meet the vertex cover in 1 or 2 vertices. It has to have at least one end in the set X, but it could also have both ends in the set X, right? And because it has to use at least one and all matchings are disjoint, all edges are disjoint, that means that you cannot have any more than the size of the vertex cover. Okay? Is that the same argument you were thinking about, Dev?
Yes.
Okay. All right. And in particular, there is a corollary of this. Before that, let me state a minimization problem. So we have a maximization problem here, right? Actually, let me remove this optimization. Let me put it as maximization problem. Let's think about vertex covers for a few seconds. Does every graph have a vertex cover? Does every
Yes.
graph have a vertex cover? Yes. Why?
You can just basically take all the vertices and that's what.
Yes. The entire set of vertices is a vertex cover, right? Because each edge has at least one end in the entire set of vertices. Okay? So V of G is a vertex cover. So from the vertex cover point of view, the interesting problem is to minimize. So we have a minimization problem. Given a graph G, find a minimum vertex cover, right? By that I mean a vertex cover of minimum cardinality. Okay? And again, the question arises, if you have a vertex cover, how do you convince someone that a given vertex cover is of minimum cardinality? Okay? I won't write it down. But here is an interesting corollary. Supposing, let G be a graph and let M be a matching and X a vertex cover. Assume that cardinality of M is equal to cardinality of X. Then what can you tell me about this matching and about this cover?
Maximum matching and minimum vertices.
Exactly. So if you look at this observation, it immediately follows that the matching has to be of maximum size and the cover is of minimum size. Then M is a maximum matching. And X is a minimum cover. Okay? Good. All right. So the question now arises, is it true that for any graph, the maximum matching has the same size as the minimum cover? You can relate this to Menger's theorem, right? It's similar to Menger's theorem. Is the maximum number of edge disjoint paths, is the maximum cardinality of pairwise edge disjoint paths equal to the minimum cardinality of a cut, right? ST paths and ST cuts. And there the answer is yes. And that is what Menger's theorem tells you. So you can ask a similar question here. Is it true that in any graph G, the cardinality of maximum matching is equal to the cardinality of a minimum vertex cover? So what do people think? Is it true that in any graph in the world, the cardinality of the maximum matching is equal to the cardinality of the minimum vertex cover? In the examples we have done so far, it was true. Let's go back to these examples. We found a matching of size 1, we found a cover of size 1. Clearly, that's a maximum matching and a minimum cover. We found a matching of size 2 and we found a cover of size 2. Again, maximum matching, minimum cover. So is the statement true in general?
No.
Consider K3
All
into one.
cycles.
Consider K3.
K3. Okay. Someone else said no. Who was that?
That was me.
Okay. So K3 is one example. What is another example?
I was also thinking of a triangle.
Okay, good. So what is the size of a maximum matching in K3? And I'm going to call out someone, okay? So let's see. Pappu, are you there? Size of a maximum matching is 1. And what is the size of a minimum cover? What is the size of a minimum cover? 2. Exactly. Right? Okay, good. Thanks. Okay. So the maximum matching is size 1 here and the minimum cover is size 2. So, well, the answer is no. Right? But it turns out that there is a class of graphs which we have discussed before where the answer is yes. And that is Koenig's theorem. For any bipartite graph G, the size of a maximum matching is equal to the size of a minimum vertex cover. Okay? So Koenig's theorem looks very much like Menger's theorem. It shows that a certain maximization problem has the same value as a certain minimization problem, right? But it only applies for bipartite graphs. Okay? And this can be proved using the Max-Flow-Mincut theorem. Not only that, using Max-Flow-Mincut, you can actually find the maximum matching, you can find the minimum vertex cover in any bipartite graph. Unfortunately, it does not work for non-bipartite graphs. And so that requires a lot more sophisticated techniques, which Meghna will be covering. But in the next lecture on Friday, I will see if we can manage to cover either the proof or at least some proof sketch of Koenig's theorem using Max-Flow-Mincut. Proof of Koenig's theorem using Max-Flow-Mincut. And not only will it be the proof, it will be a constructive proof, which means that you will be able to get algorithms for both the problems, maximum matching and minimum vertex cover in a bipartite graph. Okay. So let's see if we can complete that. But if not, then I will try to at least cover a proof sketch and I will put the proof in the type notes. Also on this note, the type notes, I have put one version of the type notes on Moodle. It is very much a work in progress because I'm struggling with time. I think the first 3 sections are complete, more or less, but I'm going to keep editing over the next week. So yeah, I'll try to edit as soon as I can find time to do it. Okay. All right. Are there any questions about what we discussed today? Anything that was not clear? Anyone who is seeing matchings and covers for the first time, would you like to have more discussion on the topic?
Thank you, sir.
Thank you. You're welcome. Number of matchings in K1. So let's think about this, Papu. So let's look at K1. what is the maximum number of edges you can find that do not share any vertex? Zero, right? So the what is a matching then? It is the empty set, right? So K1 has only one matching, which is the empty set. Yeah. Any other questions? Okay. Okay. Vamsi, are you there? Okay, well, I'm going to stop recording and remove you from the meeting.